Hey, welcome back, chemistry. Today, the goal is to get you some of the important kind of nuclear vocab that we need to be able to successfully navigate our chemistry content to this unit. So hopefully, we kind of been seeing how our atoms and our nucleus can start to change and how we can start to think about stable and unstable atoms. And really, goal today is to get you just the pieces you need to be able to start to describe that process. If at any point, as you're taking notes, feel free to pause the video. If it was me, I would pause, every time I hit the slide button, pause it, record all the notes, unpause it, and then kind of step through it with me to make sure it's making sense as we're kind of going through these different parts and kind of pieces today. If at any point you have questions, feel free to email. We'll also come back together and kind of review and make sure we're all on the same page and really start to use these different vocab pieces for the remainder of our unit. So here we go. When we think about our nucleus, we know we got our protons and our neutrons hanging out there in the center, and we got these electrons hanging outside in these outer rings. And while the rest of the year, we're going to talk about the electrons, for this kind of little mini unit, this unit 3, we're looking specifically at the nucleus and how it can start to become more stable. Because we know as we get larger and larger and larger, we get these really massive nuclei, really massive nucleus. And what will happen is it's too hard to hold all those protons and neutrons together. So we start to kind of break apart and start to spit out some of those pieces. And that's really what we're looking at when we start to talk about our nuclear changes. So here we go. Couple vocab words, nucleons being the first. Nucleon is just referring to a particle in the nucleus. So it could be protons or neutrons. It's really anything kind of hanging out in the center of the atom. All of the kind of marble magnets we use for our activities this unit, those are all nucleons hanging out together in the nucleus. Not to be confused with a nuclide. A nuclide would be the entire atom, including the electrons. And so when we say a radioactive nuclide, we talk about the whole atom. Talk about nucleons, we're just looking at the particles in the nucleus. All these nuclear, nucleus, nuclei words, but we'll get them, we'll keep them straight. If I were to tell you a nuclide has 45 nucleons, could you tell me what the element is? And you're thinking, well, 45. Well, number 45 on the periodic table, that's rhodium, number 45. But wait, that's the atomic number. That's the number of protons. This is nucleons. It's both the protons and the neutrons. And so maybe it's 22 protons and 23 neutrons, or maybe it's 20 neutrons and 30 protons. There's no way to know what the element is because we don't know specifically how many protons. We would need a little more information than that. Now we could say the mass is 45, but we don't know how many protons are in there. And so we can't quite identify just from that. But we still know how many things or particles are hanging out in the nucleus. So just a little distinction between our nucleons and our nuclei. Cool. A nuclear reaction. A nuclear reaction is any reaction that affects the nucleus of an atom. And again, I'll admit, most of our chemistry, we're not going to be doing this. We got a proton, it's going to stay, or an atom, it's got some protons, they're going to stay the same. We're just going to be changing the electrons for most of the year. But it's nice to kind of think about the nucleus and how it could change. It also has a lot of practical applications and medical applications that are kind of interesting to look at. So for a nuclear reaction, this is any reaction that affects the nucleus of our atom. And if you're going to change the nucleus, now all of a sudden you might be changing elements, right? You lose some protons, all of a sudden you got something new. You've changed your substance. A nuclear reaction is going to be one that changes the nucleus. The total number of protons and the total mass have to be conserved, by which I mean they have to be the same on both sides of the change. You can't just have protons disappearing. You can't have neutrons disappearing. We still got to account for them. But we can change for a particular atom the number of protons, which is going to change the identity of the nucleus. We call that a transmutation. For all my Full Metal Alchemist fans, it is a real thing. If you transmute an element, that means you've changed the identity of the nucleus as a result of changing the number of protons. If you've lost or gained some protons, all of a sudden your element is changing into something new. Here we've got an example of carbon-14, and it's breaking apart into two other particles. We'll notice that the mass is staying the same. We got 14 before and 14 after. Well, we had 6 protons before, and all of a sudden now there's 7 protons. But 7 plus -1, 7 minus 1 is still 6. So we still have the same mass and protons on the right as we did on the left. We're going to talk about it more in just a second. This is a beta particle, and this is getting shot out into space. And now all of a sudden we have a new element being produced, and that is transmutation. We have transmuted our original atom. Well, when you hear the word radioactivity, an unstable atomic nucleus can shoot out a form of radiation in order to become more stable. We'll talk about radiation here in just a second. But whenever you hear radioactivity or a radioactive particle, this is a particle that's going to spit out some form of energy in an effort to become stable. In other words, our nuclide, our atom, is decaying or breaking down into a different atom. And the way it does that is by shooting out some particles. Now it has less things it's trying to hold or keep together with a strong nuclear force, and we become more stable as a result of the removal of some particles. We call it radioactive decay. Radioactive decay. Cool. There are three types of radiation. And our goal is to kind of be familiar with these three radioactive particles. We're going to be seeing these quite a bit. And it is our alpha, our beta, and our gamma. No, we're not talking about fraternities or sororities. Yes, we're stealing from the Greek alphabet. We're describing our three radiation particles as an alpha, beta, or a gamma. And we're just talking about the things that are getting shot off into space. That's it. These are our radioactive particles. An alpha particle is a helium nucleus. A beta particle or beta minus particle, I'll admit, I usually just kind of shorten it to beta particle, is an electron, not from the rings, out of the nucleus, an electron from the nucleus. And this happens when a neutron turns into a proton. And then we've got our gamma ray. This is a high energy photon. And usually it's a byproduct of one of our other forms of radiation. Usually we have this beta particle shoot out, and then we get this gamma come off with it. And it's a high energy photon. Well, a photon, just a little packet of light energy. And so when we think about our different types of light on our electromagnetic spectrum, we got all sorts of different types of light energy. And so the ones we're most familiar with is the visible light here in the middle. These are the things we can see. Infrared we can't see, microwaves we can't see. We know they do stuff for us. We use them all the time. But if you look way over here to the right, we got our gamma rays. You'll notice that these waves are really, really tight together. They have incredibly high energy. And because of that, they actually kill cancer cells. They'll actually damage the human body and kind of start to destroy things because they got such high energy. And they're really hard to stop when they're that high energy light like that. We know X-rays can go all the way through the body. Gamma rays have even more energy than that, which is crazy to think about. But we'll talk about it more. Cool. If we want to visualize what this would look like. So for an alpha decay, that's a helium nucleus. We would have this kind of original atom. We're going to take two protons, two neutrons. That's our alpha particle. And we're actually going to just spit it out. We shoot it out into space. Here's our radiation. That leaves behind this smaller particle. And now it's more stable. And so an alpha particle is just the removal of kind of our two protons, two neutrons. And we saw alpha particles actually in our activity 4, or we will see them in activity 4. This is kind of a big particle we can use to start to use in our particle accelerators. Beta decay from our nucleus, not from the energy, but from our nucleus, we shoot out an electron, leaving less charge overall in our original atom. Gamma radiation is just the removal of some light energy, shooting out some of this gamma ray. We'll talk more about how we start to show this with these formulas later. Don't worry about that quite yet. I'm more concerned right now that we're kind of getting a familiarity with these different types of radioactive particles. So chemically, the way we show these are with some symbols. An alpha is a helium nucleus, 4/2. 4 being the mass. 2 protons, 2 neutrons is a total mass of 4. 2 protons means the atomic number is 2. And if you got 2 protons, that makes you a helium. Technically, should be a little 2 plus on here because there's no electrons, just 2 positive protons. But we often leave it off just to shorthand the symbol. Beta is an electron. It's kind of symbol 0/-1. And this is to help kind of keep our math working out correctly. And a gamma is just high energy light. Gets this little kind of Y symbol. It's a 0/0. It doesn't change the mass, doesn't change the protons, just beam of light energy coming out from our atom. Light energy that we can't see, which is weird to think about. Cool. Because of their size, these different particles have different degrees of damage to their surroundings. Alpha particles are pretty big, which means we can protect ourselves from alpha particles with our skin or a piece of paper. They bounce right off. They're pretty easy to stop. If you remember, alpha particles are what Rutherford used when he was kind of doing his gold foil experiment. Beta particles are smaller and moving faster, kind of like a needle dart. And so these are harder to stop. Takes about 1 centimeter of paper or cardboard. Your average book would stop a beta particle. Gamma rays are crazy fast. They're traveling at the speed of light, which means it takes all the way up to 13 centimeters of lead to start to stop our gamma particles because our gamma radiation, because they're moving so incredibly fast, speed of light. Go a little bit more on each of them, and then we'll kind of wrap this up. An alpha particle gets this little Greek symbol alpha. And again, chemically, it is He 4/2. It is 2 protons and 2 neutrons chemically stuck together, bound together. So we got our big heavy atom, takes 2 protons, 2 neutrons, spits it out, and now our atom is smaller. Our nuclide is a smaller particle, and it is more easily held together. It is a positively charged helium nucleus. It has high energy because it is pretty massive, but it's moving relatively slow. It's got a relatively low velocity. It's not traveling anywhere near the speed of our beta or our gamma particles. As a result, we can stop it with thickness of paper or skin. And here we've got our example. So we got our thorium here. And from our thorium, we pull out 2 protons, spit them out, which means we lose 2 protons. So our original thorium now has 2 fewer protons, which turns it into radium. It actually transmutes the element into something else. Because we lost 2 neutrons as well, we lost a total of 4 nucleons. So our mass goes down by 4. It's kind of the giveaway for an alpha particle. If your mass is changing, the only thing that will do that is an alpha decay. We're spitting out that alpha particle. Our mass goes down by 4. We lose 2 protons, and our element changes into something more stable and into something new. This is our alpha particle. Our beta minus particle gets the Greek letter beta. It's chemically written as E0/-1. And again, this is just to keep the math consistent. This is a high energy electron, and it's a new electron, one that wasn't there before. And what happens is our neutron, which is neutral, but made up of smaller particles, quarks, don't worry about that. You got this kind of neutral neutron. It spits out some negatives. And if it loses negative, it becomes positive. And so our neutron is going to decay into a proton. The mass stays the same, 1 AMU, 1 AMU. Our neutron spits out the electron and becomes positive, becomes a proton. And so this is why the mass stays the same. You're not losing any major mass particles. Electrons, we know, are incredibly, incredibly light, hardly any mass to them. But if we lose our negative, our neutron becomes positive, which changes the number of protons. We go from protactinium here into uranium. So we're gaining a proton, changing the element by losing an electron. And I know what you're thinking, like, wait, if we put more protons in the nucleus, it's going to make it even more unstable. Well, maybe it does that, and then it does it alpha. Losing some more particles become even more stable. So we'll start to see oftentimes we chain these together. These beta particles have high velocity, but relatively low energy. They're not very big. They have a pretty small kind of pinpoint area of interaction. And so because they're pretty small particles, we can stop them with about 1 centimeter thickness of aluminum or plastic. Your mice of men can stop these. And then we got our example down here at the bottom kind of showing what this would look like if we were to write a chemical change. Again, we got 234 on the left, a total of 234 on the right. We got 91 on the left and a total of 91 on the right. Those numbers got to add up to be the same. We've got to keep track of what's going on. Our last radiation particle is our gamma. These are the easiest to write because they don't change anything. They're just super high energy, usually coming out after a beta particle. So these are high energy electromagnetic waves, and they usually follow a beta particle. They are traveling the speed of light, which means it takes 13 centimeters of lead to actually get that light energy to stop. These are incredibly high energy. We can use these for the treatment of cancer cells. We can use these for sterilization of food or surgical equipment. A lot of practical applications for gamma rays, but it is just more energy leaving the nucleus, helping us become more stable. Coming back a little bit later, we'll talk about how we start to write these and practice these different decays. But for now, I just wanted to get you the main vocab so that you've got these for your notes to be able to start to think about how we're going to describe these nuclear changes.